After watching this video, you will understand the definition of derivatives and how we use them. Let's start with the definition. A derivative in mathematics is a way to precisely describe how a quantity changes. If the quantity is given by a function, the instantaneous change of that quantity is determined by the derivative of the function. So what we can take from this is that the derivative tells us something about how a function changes. Let's start with one of the simplest functions we have, a linear function. Here we have a linear function drawn in a coordinate system, and we're interested in how this curve changes, or in other words, how steep it is. What we know is that for a linear function, the steepness is the same everywhere along the curve. If you imagine walking up the line, the slope stays constant the entire way. But how do we measure this change, or steepness? We measure it by looking at how much the y value increases for each step we take in the x direction. If x represents meters forward, and y represents meters upward, then the steepness tells us how many meters we go up for each meter we go forward. Let's find this using the points x1, y1 and x2, y2. We measure the change in y as y2 minus y1 and the change in x as x2 minus x1. For example, moving from one point to another, we might go 3 units forward and 6 units upwards. To calculate the slope of the curve, which we denote by a, we take the change in y divided by the change in x. Since we are working with a function f, we often write the points as x1, f x1 and x2, f x2. If we plug in the values, for example 9 minus 3 in the numerator and 4 minus 1 in the denominator, we get a equals 2. This means that for every step we take in the x direction, the y value increases by 2. That was straightforward. Now let's look at a more complicated case. We now consider a 4th degree polynomial function f. Imagine this function as a mountain, where the x-axis represents distance in kilometers and the y-axis represents height above sea level. So we're dealing with quite a tall mountain. Suppose we're standing on one side of the mountain and want to walk to a flag on another peak. We can represent this as 2 points on the function. We now want to find out how steep the path is between these 2 points. Again, we measure steepness as how much we go up per unit we go forward. So we draw a straight line between the 2 points. And we now compute the change in y and the change in x. And we get the formula y2 minus y1 divided by x2 minus x1. And with function notation, we get fx2 minus fx1 divided by x2 minus x1. If we plug in these values, we get a vertical change of 6.3 kilometers and a horizontal change of 7 kilometers. And we get 0.9. This tells us that on average we climb 0.9 kilometers for every kilometers we move forward. This is called the average rate of change. But this straight line doesn't tell us exactly how steep it is where we're standing right now. So what can we do? We move the point closer to our position. Now the straight line better approximates the steepness of the curve at our location. Repeating the calculation, we get a change in y equal to 5.46 and a change in x equal to 1.14, which gives 4.79. So we're climbing 4.79 kilometers per kilometers we move forward. So this is a lot steeper. But even this is not exact. So we move the point even closer. Now we get change in y equal to 0.11 and change in x equal to 0.01, which gives 11. So we're climbing 11 kilometers per kilometers forward. We can keep moving the point closer and closer. As the distance between the points approaches 0, we get what we call the instantaneous rate of change. And this is where the derivative comes in. The derivative is essentially the slope between 2 points, fx2 minus fx1 divided by x2 minus x1, where x2 minus x1 is extremely small. Let's define x2 minus x1 equal to h, then x1 equals x, x2 equals x plus h. This gives us the following formula. As h approaches 0, we get the definition of the derivative. F derived equals lim h goes to 0, fx plus h minus fx divided by h. This means we look at how much the function changes when we move an infinitely small distance along the x-axis. Sometimes h is written as delta x, but this means the same thing. This definition is the foundation for all differentiation rules. Let's look at an example. F equals x to the third. We use the definition of the derivative and we get x plus h to the third minus x to the third divided by h. Expanding, we get x to the power of third plus 3x squared times h plus 3x times h squared plus h to the third minus x to the third. And by simplifying, we get 3x squared plus 3xh plus h squared. As h goes to 0, the terms with h disappear, leaving 3x squared. So the derivative of f equals 3 times x squared. We can now use this to find the slope at a specific point on the function. For example, at x equals 1, the derivative of f of 1 equals 3 times 1 squared equals 3. So the instantaneous rate of change at x equals 1 is 3.